Hello. So I get to talk about software architecture at a craftsmanship conference. And this is actually a talk of two halves. So although I'm doing the opening keynote now, I'll be back at 5 p.m. to finish the keynote. So I'm going to leave you in suspense. And I apologize in advance, but this first session is going to break the first law on the board. Speakers should show or write code. I'm not doing that this morning, but I will do that this afternoon. But I worked in London for most of my career building software. And over the past few years, I've been kind of jetting around the world and really helping teams understand what software architecture is all about. Software architecture has a bad reputation. People don't like it. They don't like architects. So I've been trying to reverse a lot of that trend. And really, my whole picture is that architecture needs to be much more accessible to us as software developers. Has anybody here tried to read any of those classic architecture books? The really big, thick ones? Did you like them? People are doing this. That's harsh. Those books are very, very good. The authors are fantastic, but those books tend to approach architecture from a very academic and research perspective. And so when I was moving into my first tech lead, team lead architecture roles, I didn't really understand how those books related to my day-to-day work. So how do I fix this problem? Well, I wrote my own book. That's obviously the thing you do here. So hopefully this is, it's helping people understand what software architecture is about. Now, I still do write code. So I'm not one of these kind of fluffy, hand-waving style architects. I do write code. And actually, that's really important because what I'm really interested in here is the intersection between code and architecture. Right? So how do these two worlds meet? And that's basically what it talks about. So my specific interest here is how do we, as developers, share our ideas? How do we visualize our architecture? How do we communicate our architecture? So before we discuss that, let's look at the tension between architecture and code. Anybody here drawing architecture pictures as part of their day job? Right, that's a good chunk of you. So there are lots and lots of different ways we can draw architecture pictures to describe the design of our software. And one of the things you learn really, really quickly is that it's hard to show everything on a single picture, a single piece of paper, because we want to show so many different things, don't we? And this is why when you do read those classic architecture books, they'll talk about views and viewpoints and perspectives. Here's an example. This is Philip Critchton's 4+1 architectural view model. And he basically says this: to describe a software architecture, we use a model comprised of multiple views or perspectives. So this is essentially slicing up how we view the system so we can show different things at different times. This is Philip Critchton's 4+1 model. There's a logical view up here, which kind of looks like modules and services and functional things. On the right, we have the development view, which is aimed at software developers. It's really about the structure and organization of the code. Process view is concurrency stuff, and the physical view is really about processes. And these are all tied together with use cases and scenarios and requirements. This is just one approach. There are lots and lots of other approaches. And the thing you'll notice when you start comparing different approaches to describing software systems is that they all conflict. So although we've got logical view, development view, process view, physical view on this picture, when you read other approaches, those words will mean different things. And that's really confusing. So I've been in meetings where architects have argued with me that there's a difference between a conceptual view of my system and a logical view. And I'm like, what? That doesn't make any sense to me whatsoever. What's the development view? The development view is normally about the code, but some people call that the design view. Other people still call it the implementation view. Who's using physical hardware here? It's like one sort of a bit, two. So why do we still have a physical view? Shouldn't we have a virtual view to map out our cloud environments? You know, some of these names just don't make sense anymore. The thing you will notice when you look at these different view catalogs is that they have this clean separation between the logical view of the world, modules and components and services and subsystems, and the code. Right? There's a split. And that's where a lot of this tension comes from. If somebody asks you to go draw an architecture picture to describe your system to other people, you have to wade through all of this stuff. Which view do I use? What notation do I use? How much detail do I go down to? And that just makes my head hurt. Do you guys know what brain freeze is? It's that thing that when you eat ice cream really fast, it makes your head hurt somewhere here. Now, I've got 2 children, 11 and 8, 2 boys, and they love ice cream. And every time they eat ice cream, they go, "Oh, Daddy, brain freeze." I'm like, well, stop eating ice cream, or just slow down. Now, if you go to the Wikipedia page about brain freeze, there are some workarounds to avoid this situation. For example, having a hot drink before you eat ice cream. That's apparently a workaround. It's not going to work with my kids. The other approach is to just not eat ice cream. Try telling that to my kids. So let's do something else. If all of this view stuff makes my head hurt, let's just not use it. Let's cheat. Because as developers, we like cheating. What do I mean? Well, let's go to Google. Right, so let's go and ask Google what a software architecture picture looks like. If you've ever done it, you'll see it's stuff like this. It's page after page after page of basically colorful block pictures. And if you zoom into these things, you get stuff like, oh, it's horrible. Who's using UML here? Oh. That's approximately 0. There were some UML pictures on that Google screenshot, but most people don't seem to be using UML anymore. And I've asked this question all over the world, and I get the same sort of feedback. So this is why people draw these horrible diagrams. And these are exactly the type of diagrams that I see when I go and visit organizations, and I look through their wiki pages and their documentation sets. And if we take this one here I've highlighted, right? So when we talk about architecture, we talk about layers, and layers are a good thing. So we always have diagrams with layers. Why are some of these layers here different heights? Is that significant, or did the person drawing this not know that in Visio there's a feature that makes boxes the same size? Possibly. Why are the layers different colors? I don't know, but at least they're gradient shaded. Enterprise architects love that stuff. You'll notice we've got vertical layers that stop the diagram wobbling, because some stuff we can't fit into these nice, neat horizontal layers. We've got acronyms. Does that thing talk to that thing? I've no idea. Right, but the same pattern's repeated over and over again. It's just horrible. So people really struggle with this stuff. Over the past 6, 7, 8 years, I've noticed that people really struggle to draw pictures of their system, to describe their system. And I'll give you some more examples. So this is a real diagram from a real workshop I ran. The central spine outlines the major steps in the process. That's kind of okay. That box there, that circle, is important. Why? Because everything's pointing to it. And there's also a clock pointing to the important thing. It's like Amsterdam Schiphol or London Heathrow. It's like a big airport hub. On the other side of the diagram, it's just a mess. We've got different colors, boxes, lines, types of arrows. That box over there says UI upside down. Do you know why? Because the people drawing this were sitting at a round table, and they were just writing from wherever they were sitting, basically. It's laziness. Another one for you. This diagram doesn't tell you anything. This basically says we're building a system, and we do auditing, and we look after errors, and we have a scheduler, and we generate some reports. And look, we do business logic. Wow. This is like every system I've ever built in the world. Another one for you. You've heard of POJOs, plain old Java objects, and POCOs, plain old C# objects. There's a homeless edition that nobody tells you about, the HOCO. This is a Microsoft solution. At the bottom, there's a SQL Server database. At the top, there's a box labeled application, and it's annotated console C#. So it's a console application, a public static void main app. What's everything else? We've got lots of boxes on here, calculation things, and manager things, and loader things, and they're all annotated C#. It's just a weird diagram. We have a bunch of floating C# things talking to a SQL Server box. I think what this diagram is really trying to say is there's an application talking to a database, and that's it. And all of these boxes live inside that application. But that's not what the diagram says. There's a top and bottom that I missed off because it would just hurt your eyes too much. When I was a kid, we had these storybooks, and you'd start from page 1, and you'd read through a few pages, and you would get to basically a fork in the story. And you, as the reader, could decide which way to take the story by turning to different pages in the book. This diagram is the same. You start at the top, go down. Eventually, you get to a point where you have to make some choices. Do we follow the fail event, or the complete event path, or the reject event path? Now, when I was reading these books as a kid, my character always died. Really annoying. If you just stare at this diagram for long enough, you will also die. Because, look, all paths lead to that trap. There's no way out. The thing I love about this picture, look, calculation engine A plus B equals C. We're adding 2 numbers up. This is a microservices architecture for adding 2 numbers. Don't laugh, this is what you'll be building next year. Right, so enough diagrams. What is it we're trying to do here? So if I'm drawing pictures during an upfront design phase, I want to ask this question. Right, here's a picture of something. Is this what I think I'm going to build? If I'm drawing pictures to describe something I have, that's the question. Is this reflective of what we built? Now, let's imagine that you inherit a code base of 1 million lines of Java code. How would you draw a picture of that system? Well, okay, let's say that that 1 million lines of Java code is actually 50,000 Java classes. Would you have a whiteboard picture with 50,000 boxes on? Therefore, allow us to reason about a large or complex software system. So we get a nice overview of the whole thing in one go. Now, this raises a kind of interesting question, I think. Does your code reflect those abstractions? So let's imagine that you have some diagrams on the wall showing components and services and layers, and you have your code. Do the 2 things match? Who thinks this is true for their organizations, their teams? A really, really scarily small number of people, like 3. So if you have diagrams on the wall and the diagrams do not reflect your code, what's the point in the diagrams? Are they just pretty? Is it because you have some really ugly wall you want to fill? Why does this happen? Well, it could happen for a bunch of reasons. I mean, maybe we don't have architecture pictures. But I think it happens for a different reason. I think it happens because when we're having architecture discussions, we're using terms like component and module and service and layer. But when we're writing our code, we don't have those concepts, do we? Show of hands, who's a Java developer here? C# developer? Right, so that's the majority of people covered here. In Java and C#, there's no component keyword, is there? You can't do public component X, public service Y. There's no layer keyword. There's no ports or adapters keyword. So we're having to create these concepts, these abstractions, based upon gluing lower-level building blocks together. And that's where this clash of concepts comes from. So let's go back to code again. So how do we normally organize our code? Well, this is a fairly standard layered approach, right? So horizontal layering. People doing this? Yeah, to some degree anyway. So imagine we're building a web application consisting of controllers and services and data access things. Basically, we have a layering strategy where we package all of the similar things together. So we have all of our controllers together in one package or namespace, all of our services in another, all of our data access objects in another. A fairly simple pattern, and this is kind of what people tell us to do. Why? Because it's in the books. Right, so here's a diagram I stole from a Spring book. It basically says, Spring is a great framework in the Java world. This is how you should build your apps. It shows you essentially a layered architecture. You flip the page, and it tells you why. It's about separation concerns and isolation and modularity and things like that. You download some sample applications. You pull them into your IDE, and guess what? It starts out with a layered structure. one folder, one package per set of things, controllers, services, domain objects, whatever. Same in the .NET world. You download ASP.NET MVC, same thing. There's a folder per category of stuff. Now, our intent with layers is all beautiful. And our layers all start out nice and clean, don't they? So our controllers only call the services, and our services only call the data access object. But guess what happens when you want to add feature set C, and it needs bits of A and bits of B? You get a bunch of options. You've seen this before, haven't you? This is how your nice, clean layered architecture evolves into that horrible big ball of mud. Now, one of the reasons this happens is because in Java especially, in order for these things to be callable by these things, that stuff needs to be public. So what we find with layered architectures is that lots of our code is public, and that means it can be called from anywhere. Now you might be thinking, Simon, layered architectures, we don't do that anymore. We do hexagons, we do ports adapters. Guess what? This is just a layered architecture. Sometimes this is just a layered architecture where people have moved the repository interface into the domain package. That makes it worse, right? Because then we get this horrible corruption of stuff. So should we be considering layers as a harmful thing? No. There are lots of really great examples about layers around the world. Different types of things. So the layering concept itself is sound, but maybe it's the way we're using it which is wrong. Maybe layers are not our structural building blocks. Maybe layers are just an internal implementation detail of something else. Is this the only way? No, there's another way. We can do package by feature. So we take our traditional horizontally layered system, and instead of having layers per controller, service, data access layer, we go the other way. So we bundle all of the things related to feature A into a package or namespace for feature A. Same with feature B. This kind of turns your code base inside out. Makes it really easy to see the main concept, but now you have to dig around to find the data access objects associated with feature A. Well, we've got good ideas, it doesn't matter. Does this solve those problems I spoke about earlier? Not really. Just gives you a different approach. If you want to add feature C and it needs bits of A and B, guess what happens? You have to start making stuff public again, so it's externally accessible. So, we talked a bit about architecture, and we talked a bit about code. And when I'm talking about code, what I'm really talking about here is the organization of the code. Right, how we organize those constructs into projects, solutions, namespaces, and packages, and how this clashes with the architecture view of the world. Now, there are some smart people out there, and this problem, this issue, has been identified before. There's a great book by George Fairbanks called Just Enough Software Architecture, and in his book, he writes about the model code gap. Essentially, it's exactly what I've just spoken about. So there's when we look at the architecture of a system, we're talking in terms of components and services and layers and things like this. And when we're looking at the code doesn't contain those constructs. So this is an identified gap, but not many people are aware of it for some reason. Let's backtrack for a second. It's 2015, right? I hope so. It's 2015. Why are we still drawing pictures manually in tools like Visio? Why can't we just auto-generate diagrams that describe our software? Has anybody tried this? What happens? It's just, you just get a mess. Why? Because of exactly the same problem. The diagramming tools, the static analysis tools, they don't understand what a component is. They don't understand what a layer is. They just see classes and interfaces in namespaces and packages. And basically, they just say, here's your code, it's a mess. And there are lots and lots of tools out there that do this. So one of my friends, they inherited a big old C#.NET system, and they threw some of these tools at the system, and the tools crashed. So they wrote their own tool. And their tool worked, but it basically says, you have a mess. Like, well, yeah, we knew that 3 months ago. So these diagramming tools, what they normally do is they give you a view of the namespaces and packages, and they consider those your top-level kind of artifact, and then you double-click, and then it shows you the classes inside them. And it links up all the dependencies. And it shows you if you really do have that big ball of mud. Right. So that's what I've set myself up to fix, all of that stuff. So how do we do this? Well, let's backtrack again. How do we describe architecture? How do we describe the design of our software system from a nice abstract high level? In the classic architecture books, they all use this terminology, modules and components and connectors. Does anybody use this terminology? There's a few people going sort of half-heartedly, yeah, a bit sometimes. In my experience, this terminology isn't that well understood. It's not that well used. And I think it's too complex. And I'll give you a really good example. I did a workshop a couple of weeks ago, and this is something I actually heard one of the teams say. So basically, I give people requirements, say, go design a system, and during the discussion, this is a component of our system, said one developer, pointing to an entire web application. I'm like, you're treating a web application as a component? That's a big component. So although these words are being used, sometimes people have different meanings and different understandings. Nobody's using UML. UML is like the one standardized way that we have to describe and share information about our software systems. But if we're not using it, it's pointless. And I think UML is not being used for a bunch of reasons. It's complex, it's too low level, it's not evolved to meet the paradigms of the systems that we're building now. And it's just a big learning curve. So let's forget notation for a second. Let's make sure that we have a common set of abstractions that we can use to describe a software system. And actually, that's what I think is more important. Let's create a common vocabulary. We talk about ubiquitous language and things like domain-driven design, but we still don't have a ubiquitous language to describe the structure of our software system. And that kind of bugs me. Now, if this sounds a bit foolish, given all the work that people have put into UML, let's go and get 2 maps of Bucharest and lay them out side by side. Those 2 maps of Bucharest will show the same things, the same abstractions. They'll show the various sectors and the old town and the other districts and the major roads and the points of interest. But guess what? Those 2 maps might use different notations, different colors, different symbols. How do we, as readers of those maps, decipher the notation? Well, there's a key on the corner. Brilliant. Right, it's a self-describing notation, so let's use that concept and apply it to software. So how do I do this? Well, very simply, for me, a software system is made up of a bunch of containers. Now, a container is very simply something where you can host code or data. In real terms, it's a web app, a Windows service, a file system, a database, something like that. If we open up those things and look inside them, for me, a container has a bunch of components running inside it. What's a component? Well, for me, it's just a relation, a bunch of related stuff with a nice, clean interface. It's like single responsibility principle taken up a level of abstraction. And because I mostly deal with Java and C#, my components are made up of classes. Right, that's it. It's just a really, really simple tree structure. And with this tree structure in mind, we can then draw diagrams at each level in turn. So I'll start out with a context picture to show the system at a high level and how it fits into the rest of the world. I'll then kind of do the pinch to zoom in to show the containers inside it. This is, browser talking to web app talking to database. I'll then pinch to zoom in again to show the components inside a particular container. And then optionally, and I rarely do this, I might do some class level modeling. Jersey's a small place. When I moved back there 6 years ago, I found it really hard to find other software developers. I know that sounds crazy in a small island, but I found it hard. So when I did find other software developers, especially those who were blogging and tweeting, I kept a list of them. That list eventually became a site I called taketribes.je. It's a basic content aggregator. It lists local people, businesses, blogs, tweets, events, and things like that. This is a context diagram for my tech tribe system. Right, so that's my system there. It has these types of users. You can call them roles, actors, personas, however you want to model people. And these system dependencies at the bottom. So we're pulling data in from Twitter, profile information, tweets. We're pulling in people's repositories from GitHub, and we're subscribing to people's blogs. Right, nice high-level picture. If this is interactive, we pinch to zoom in, and we see the containers that make up that system. Everything inside that red bounding box is my system. That's what I'm building, what I'm responsible for. People at the top, systems at the bottom. Basically, all this picture says is, look, there's a web application, and it allows our users to get access to stuff. There's a standalone content updater thing at the bottom. In this case, it's a Java 7 process. And it's a thing that reaches out to Twitter, GitHub blogs, and pulls that data back. Where is the data being stored? Somewhere in that middle trio of boxes. There's a MySQL database for storing that stuff. There's a MongoDB store for storing tweets and blog posts. And there's a file system in the middle. That's it. This diagram does not tell you anything about clustering and availability and redundancy and all that stuff. If we were to now pinch zoom into that box, we see the components inside it. So this is the component diagram for that content updater. Again, red box, everything inside that red box lives inside the content updater. The content updater reaches out to the outside world. That's why I have the systems back at the bottom. And it interacts with these other containers at the top. And basically, all this diagram says is, look, our content updater is made up of a bunch of components. There's a scheduled content thing, there's a bunch of connectors, and some components that store stuff in data stores. That's it. Tech choices, responsibilities, nice simple notation. In order to show you some pictures, I've had to create a notation. I don't want to create a standard notation. I'm trying to create a notationless notation. I'm trying to create something that works really easy with whiteboards and sticky notes and that kind of thing. So don't worry too much about the notation here. That's not what I'm trying to show you. It comes back to the concepts. I was introduced to something called Sneiderman's Mantra recently. It's a way to basically, imagine you have a massive amount of data. How do you drill down to find the data that you want? You get an overview first. That's what the context and containers diagrams give you. You then zoom and filter. So we're doing that pinch zoom movement into a container. We're filtering out the rest. And as developers, if we want the detail, we can get that on demand. It lives in the code. Yeah, they're maps. Right, that's how I use the pinch zoom thing. These are maps. If you go to your smartphone and open up Google Maps and do a search for Jersey, you'll get that. Google Maps zooms straight in. If you've never heard of Jersey, this is basically pointless. So you have to do the zoom out movement to get to the map of Europe. Similarly with the technology stuff. Sometimes as developers, we want that view of the world, the zoomed in view of the world, and other times we want to zoom out. Why? Because there are different target audiences, essentially. I'm not saying you should only draw these types of pictures. Right? There are a bunch of other ways that you want to think about and describe your software system. But what I'm trying to do here is basically look at the static structure. And if you do want information about those other views, Philip Crichton's model is a good starting point. And the Software Systems Architecture book by Owen Woods and Nick Rosansky is another great way to look at how you can describe software systems. But my approach, my C4 model, is basically looking at the static structure first. That's my primary concern here. And it's the static structure from the code through components, containers, and up to the top level of the system. It forms a really nice core and a way to describe a bunch of other things. And once you have the static structure understood, you can then weave other things around it. So, for example, you can show sequence and collaboration diagrams based upon the interaction between components. You can show how your containers map to infrastructure. That's your deployment model. So the C4 stuff is about static structure. static structure is essentially about code. Why is this important? It's important because actually, I firmly believe that we as developers are the most important stakeholders of software architecture. Right, we are the primary consumers of software architecture. So let's bring architecture back down to earth, and let's make sure architecture reflects code. Right, I've been using this term component a bit. And I already said that people have very different meanings of this word. So let's briefly look at component before we wrap up. What is a component? I'm going to show you some code, sort of. But I will show you some more code later. Spring MVC, popular framework for building web apps in the Java world. And there's a sample application called the Spring Pet Clinic. It's a really basic, user uses a web application, gets some stuff out of a database, shows you information about vets and stuff like that. It's not very interesting, but it shows you how to use Spring MVC. That's how the Spring guys describe their system. So basically, there's a bunch of stuff running kind of in the browser, HTML and CSS. And then inside their Java app, there's a bunch of controllers, a bunch of services, and a bunch of repositories. It's a fairly standard layered architecture. If you download the code and load it into your IDE, that's kind of what it looks like. So there's a bunch of domain things there. There's a repository package. That's that stuff there. There's a service, a bunch of utils. We always have utils. And there's a bunch of web stuff here. So let's imagine I am new to this system. How do I draw a picture of this system? Well, if I'm using IntelliJ or Eclipse or another tool, we could generate a class diagram automatically. And if you do that, you get that. Now, when I was showing this picture before, people said, Simon, you should have spent 5 minutes dragging the boxes around to make sure nothing crosses over. It's an impossible task. Right? I got bored really, really quickly, so I just left this diagram in here. This is a small system. Right? How many classes are there? 20, 30? That diagram is basically pointless. So if auto-generating diagrams doesn't work, how do we fix this problem? Well, actually, maybe we can just remove some of these classes. So let's take that approach first. Let's try and remove some of the detail from this picture. If we go back to our screenshot of the code, which one should we remove from the picture? Well, if I want to describe something about the design, the structure, the architecture, let's try to only show those classes that have some significance from a structural perspective. So, web. Are our web controllers structurally significant? Yeah? So that sounds good. Are our util classes structurally significant? I hope not. I hope not, but let's ignore those for now. Let's assume they're not. The service, is that structurally significant? Yeah? The repository stuff, the data access, sounds structurally significant. What about the model classes? I'm going to say no. Some of you might disagree, but once you look through these model classes, they're just data containers. So actually, they're not structurally significant. So let's take the model classes and the utils out, and let's draw a different picture. Now I can spend some time to drag the boxes around, because we're showing fewer things. This is still a small system, but it's a much cleaner picture. And now we can actually drag the boxes around to recreate that layered architecture. So look, we've got controllers at the top. We've got this middle bit, which is our service. And at the bottom, we've got our repositories. What have I had to do to make this diagram work, apart from dragging the boxes around? I've had to show both the interface and the implementation class to recreate the dependency graph, haven't I? So the interface shows you what services that thing provides to the world, but it doesn't show you what it depends on. So if you look at the clinic service, everything depends on the clinic service, but look, there are no outgoing dependencies from the interface. There can't be. So I've had to show the implementation, and then that brings us back to the other repositories. Once you show the repository implementations, you actually see there's a bit of nesting going on down here. So this is a much better diagram, but it's still showing me classes and interfaces. What I'd really like to do here is plug this into a Google Maps interface and do the pinch to zoom out. Just one notch. I want to zoom out very, very slightly. And essentially what I want to do is draw a picture that looks more like that. Do you see what I've done? I've basically merged the interface and the implementation and just called them a component. That's a much, much easier to understand picture, particularly if you now have a much, much bigger system, a much bigger code base. So how do we do that? And ultimately, how do we get to a picture that looks like that? So that's the same picture, drawn in a slightly different way. So that's our set of web controllers, that's our clinic service, and that's our set of repositories. And it shows the wiring between the repositories. So that's the problem I'm trying to solve. And that's where we finish. I'm going to leave you with a cliffhanger. And at 5 o'clock, when we come back, and feel free to use the law of 2 feet if you want to. I won't be offended. I'm going to look at how we can do this. I'm going to look at how we can extract that model from the code automatically. Because after all, if we have a code base, we should just be able to extract a bunch of that stuff from the code. I want to look at how we can create living documentation. This is something that Cyril's looking at in his workshop. You know, we spend far too much time writing manual documentation. We should be able to get as much of this in an automated fashion, in a really, really simple way. And then people can have documentation for their systems. There's a really interesting relationship between architecture and coding and testing. And I'm going to explore that in a little bit of detail. And that might upset a few of you. Because one of the things I'm going to say is don't do unit testing. So again, you'll have to come back or harass me later to understand why I'm going to say that. Will I talk about microservices? Everybody has to talk about microservices, don't they? I'm going to throw a little bit of microservices in right at the end. Because again, that's actually fairly important. And we're going to answer why are we doing all this anyway? Right? What's the point of all this? Why do we want nice, clean architectures? Why do we want architectures that are easy to change and adapt to maintain? And I'm going to show you some code. So that's me done for now. Thank you very much. See you later on. Enjoy the day.